Hey guys, here we go again. So today we're going to be looking at buffers and pH curves, as in monitoring the pH when you add acid to an existing base. I think what I should have said is not pH curve, but pH titration curve. I'll make sure to put that in your notes just to make it, better, okay, more understandable. What's pH curve? What is that? Doesn't pH has a curve? No. I'm talking about titration curve, and we'll see what that is later. Next class, you'll be making one of these. So let's talk about buffers. Okay, what is a buffer? Well, if you have a solution, and this solution has a certain pH. Let's say this solution has a pH of, let's say, 6. It's a little acidic, and you want to keep it at 6. You don't want to mess around with this solution. But you know for a fact that there are factors that will mess around with this solution, like somebody might drop some acid in there. If that happens, this number is going to drop. Some people might decide to add a base in here. If that happens, this number will rise. Well, we don't want it to rise. We don't want it to drop. We want to keep it stable. The question is, how do we ensure, or how do we keep it stable? Well, very simple. You do that by adding a buffer solution in there. Okay? Because you need to understand how pH work. pH measures the concentration of H plus, okay, inside a solution. Indirectly is also looking at how much OH minus is inside the solution. If somehow or some way some H plus got in here, pH will drop. But if you have a buffer in there, the buffer will say, hey H, what are you doing in here? Let me take you away so you don't mess with this number. Or the buffer solution might say, hey OH, what are you doing in here? Let me take you away so you don't mess with this number, so this doesn't go up. So that's kind of like the basic idea of what a buffer does, is to stabilize the pH of an already existing solution. The question is, what is it made out of? Well, it's very simple, okay? A buffer is composed of two components. One component is a weak acid. The second component is the weak acid's conjugate base. Now let me show you what that is very quickly, but what you need to know here is that the amount of weak acid and the amount of conjugate base has to be equal. Okay? So it's an equal molar amount. So this is going to be 0.5. This should also be 0.5. And later on in this note, I will show you how to prepare one of these things on paper. Now, let's take a look at this reaction. Okay, this is a simple reaction about, acetic acid in an aqueous environment. We've seen this before, and you can see the fact that this is an acid. This water right here is acting like a base. Acetate is acting as a conjugate base, and hydronium is acting as a conjugate acid. So here's a buffer solution that you can already identify. This is a weak acid. This is its conjugate base. If somehow you can get this guy and this guy together in a solution of some sort, which again I will show you later, you have a buffer. And that's really that simple. Because these two individual and a solution have the capability of saying, hey, H, I can pick you up so you don't mess with this number. This guy can say, hey, I can pick you up so you don't mess with this number. That's how we buff. Okay, so here's a little schematic diagram showing you how to make a buffer solution. Okay, so you take some weak acid, in this case it will be acetic acid. You take some conjugate base of this weak acid, which is in this case the acetate, but of course you don't pour in acetate, you pour in sodium acetate. Has to be a real compound, man. Okay, the reason for this is very simple, of course. Acetic acid inside a solution, once it's in water, you mix some acetate, of course, and this guy fully dissociate. Okay, Na sodium acetate right here actually fully dissociate to give you Na plus, which will do nothing to the solution. Okay, it will not change its pH because this is a metal that can make up a strong base. Plus acetate. Okay, so that's how you prepare your conjugate base to mix with a weak acid to make this buffer solution. And this is what's inside the buffer solution. So inside the solution, you'll have obviously acetate, which we saw here. Okay, you'll have some acetic acid that is undissociated because remember, these are weak acids. Weak acids, like this equation, are predominantly this way. So when you add acetic acid to a solution, you're going to get more of these, which are undissociated, than these, which are dissociated, which means you're not going to make a lot of these, but you will have some of it. Okay, as you see, there are some H3O plus and some Na plus that really they're not really contributing to anything. Okay, this guy, however, is contributing the overall pH of the buffer. So you can see that this buffer solution made out of acetic acid and sodium acetate is going to be slightly acidic. That's just the way it is. So this is known as an acid buffer. The question is there a base buffer? Can you make a buffer that is slightly basic? Absolutely. Okay, let me just show you very quickly how to do that right here. Okay, let me show you the chemistry behind it. First, you need a weak base. So this is a basic buffer. Okay, because this one is an acidic buffer. So let me show you how to make a basic buffer. Let me think of a weak acid that you guys are... Oh yeah, this one. There's a weak acid, right? That we all can agree that it is a weak acid. When you put that in water, you're gonna establish an equilibrium reaction of NH4 plus and OH minus. As you can see, it is the OH minus right here that contributes to the basic nature of this buffer. However, you're not going to get a lot of this because this is a weak base, and in a weak base, the equilibrium shifts more towards this way, where this guy is not going to be accepting that much proton if you think about it. Okay, so here's your weak base. So what about your conjugate acid? So here's your weak base. So let me just write that down here. For a basic buffer to exist, you want to mix a weak base with this conjugate acid. Okay. And the conjugate acid will be this guy. This guy is the weak base conjugate acid. But obviously you cannot just say, hey, why don't I just put this guy into my beaker and call that a buffer? No, you're not making no buffer here. If you put this in a solution, you're just making a weak base solution. You're going to have to somehow mix this, okay, into this already existing solution, and there's just one participant, ammonium chloride. Okay, so if you add ammonium chloride into your beaker, because ammonium chloride dissociate completely to ammonium and chloride ion. It's very important that you pick chloride because chloride is the anion of a strong acid, like hydrochloric acid. So this guy is not going to do anything. Just like how we see sodium here doesn't do anything because sodium is the metal that makes up a strong base. Chloride is the anion that makes up a strong acid. So when they're strong, they're not going to play a role. They're not going to mess around. All right. There you go. You just made a basic buffer. So all you have to do is put this and this, okay, inside a beaker, okay, full of water. And what you have yourself a basic buffer. But remember one more thing, okay, and that one more thing is that you want to make sure that they are in equal molarity. But it's really easier than said and done, okay? So, you've seen how to make an acidic buffer and you've seen how to make a basic buffer. So let's take a look at how buffer buffs. This is a very, very important, I guess, diagram. We're using the acidic buffer. Okay, here's your acidic buffer. We're using this to show how it buffs. Okay, so what you see here is the weak acid. And what you see here is an equal amount of the conjugate base of this weak acid. So, let's say some dude add some HCl into this. Oh my God, why would you do that? Okay, well, no matter at all. HCl dissociate to give you H plus and Cl minus. Okay, this guy right here. Let me just get rid of this circle. Okay, you have to look at this as a whole. You can look at this as a whole. Okay, not separate, as it really shouldn't have a separation. So if you add HCl into the buffer solution, or in a solution that contains the buffer solution, HCl will dissociate completely to give you H plus and Cl minus. This H plus here will increase the concentration, will increase the, the acidic content of your solution, causing your pH to decrease. Well, you don't want that. You want your pH to stabilize. So this guy comes into play. Okay? Because the acetate will say, hey, what are you doing here? Well, guess what? I'm going to pick you up. By me picking you up, you are not messing around with the H plus concentration in this beaker, and you're not making my pH go down because you and I will perform this reaction. We're going to turn ourselves into acetic acid. However, you know me, we don't dissociate that often. So that way, all these H that you dropped in here, I pick you all up so you don't mess around with the pH. Pretty neat, huh? Well, what if you add sodium hydroxide in here? Because sodium hydroxide dissociate to give you Na plus and OH minus. OH minus have the ability to raise your pH. Well, that's when this guy comes into play. This guy is going to say, hey, OH, what are you doing in here? I don't want you to be in this solution so you can raise my pH. That's not what I want you to do. Well, guess what? We're going to hook up and we're going to put a stop to that. Because HCH3, COOH, can combine with OH minus to form, well, OH minus will pick up this O. Let me draw a little heart here. Okay? And make water. Plus acetate. Okay? See? You drop OH in here, no big deal. I will pick it up and turn it into water, which is neutral. And I'm going to make acetate. No big deal, because, hey, my buffer solution has acetate anyway. Just like in this case, making acetic acid. No big deal, because my buffer solution has acetic acid in it already. So hopefully you can see how buffer buffs in a way that it has the ability to pick up H plus and pick up OH minus. Now obviously there is this limit. If you keep adding this in here or you keep adding this in there, there will be a point where, of course, this buffer solution says, I don't have any more things to buff. Well, I guess the pH will have to go up or go down. Okay. But why would you do that? All right, so this diagram kind of shows, rather my little illustration, it shows, of course, in a bar chart of how when you add acid in there, so you're really adding H3O, that acetic acid, which is this, will go up, okay, while this will come down, okay? And same with the other side, that if you add OH to this, obviously looking at this reaction, you will make more of these, so this will go up, while this, of course, will come down. Okay. I hope this is certainly something that you understand and be able to interpret. Now, this is actually done with an acid buffer. Okay. How would it work if you have a base buffer? So remember earlier in the previous slide, we made a base buffer consisting of NH4 and NH3. Okay, remember this buffer? Well, same idea. Okay, let me just use some color. If for some reason you add some acid in there, okay, so obviously what you're dropping in there is H plus, then NH3 will come into play because NH3 will say, hey, H plus, let me take you away to make myself NH4 plus. All right, and let's say you add sodium hydroxide in here. What would the basic buffer do? Well, now this guy comes into play and say, hey, OH, what are you doing here? I'm gonna turn you into NH4OH. Okay. Or in this case, actually, no. It's not going to do that. It's not going to do that. It's a better solution. Okay, and that better solution is take one of these H's and put it in here. And instead you make NH3 plus water. Okay, not making NH4OH because NH4OH would just dissociate again to give you. You see, if you make this, it actually won't make that because this reaction is unidirectional. Okay, it's little mistakes that I kind of made, but at least I corrected myself this time. But so if you add NaOH in there, okay, obviously you're adding OH minus. NH4 will say, hey, let me pick up those OH minus, okay, by accepting one of these protons to make NH3 and water. Okay, so that's what OH minus will do, because OH minus is a base. It accepts proton in nature, and it will accept it from this guy, turning him into NH3. So, I hope you understand exactly how this works, because it's sort of fascinating how buffer works, because we put buffer in a lot of things. Okay, we actually do, to stabilize pH. You know, one of the more important thing about buffer is that there's buffer in your blood, naturally, in a form of carbonate. Okay, carbonate is actually inside your intestine, your small intestine, the beginning part of your intestine, made by your pancreas. Why are they there? Well, it's because after when you eat a lot of food, after when food is being treated in your stomach produces a lot of acid. Okay, so your food is actually mixed with this very soury substance that contains hydrochloric acid. So it's very H+. And it's not very comfortable, let's just say, if that acidic, what we call chyme, is inside your small intestine. It will hurt. So to stabilize the pH of your small intestine, you know, there's bicarbonate. I think I said carbonate earlier. There's bicarbonate inside your small intestine, produced by the pancreas, that have the ability to pick up those H+ from your chyme and turn it into H2CO3. And you know how this is unstable. This will actually decompose to give you water and CO2, which is good because you always need water. And guess what you're going to do with this CO2, huh? Huh? You know, making gas in your gut? Where would this gas go? It can only go one way, and it makes a very funny sound every now and then. You know what I mean. But that's, you know, that's what happens. There's obviously buffers in your internal system. Okay, not just in the digestive tract, but as I said, there's it's also in your blood too, to keep your blood at a slightly basic environment. All right. How do you make one of these? That's the question. How do you make one of these? And how do you ensure that the amount that you make is equal in molarity? There's two methods. Let's take a look at method 1. And then we'll move on and look at titration curve. So method 1 is, you want to make, let's say, an acidic one. Okay, you want to make an acidic buffer. So the best way to do it is to take acetic acid, okay, and you react this with sodium hydroxide. But don't make them equal. Maybe if you're going to make this 1 mole, I don't know, make this only half a mole. Okay, so it's half the molar concentration of the acid. Now, this will establish an equilibrium reaction to give you this salt. that dissociate all the time, and water. Okay? Now, how is this a buffer solution? Well, watch this. In the beginning, of course, you're not going to have any of these. But as you let these guys mix, okay, they will establish an equilibrium. They will, okay? This, being the limited reagent, will take half of these and make half of these, if you know what I mean, because you can see that the ratio here is 1 to 1. If you have 0.5 mole of this is going to react with 0.5 mole of these guys to create 0.5 mole of this and 0.5 mole of that. Simple stoichiometry, right? So if you have 0.5 mole of this limited reagent, sodium hydroxide, you're going to take away half of these because these guys are 1 to 1. So let's write that in, okay? The change here is that you're going to lose half of the acetic acid, okay? The reaction here is that you're going to use up all the NaOH because NaOH is limited. The salt will gain because obviously you're combining all of this with half of these to make this. So it's half a mole, and of course half a mole of the other guy too. Can't forget about the water. So as a change, you can see that, oh, look, you get half a mole of acetic acid. You use all of this up, okay? And look, you have half a mole of acetate. Remember, this guy dissociates, okay? And of course, you have half a mole of water. There you go. You made your buffer. There's your buffer solution. Equal amount. Pretty sick, huh? And of course, you can do the same thing with a base. Okay, so let's do another method. So here we go. Method 2. Okay, this time I want to make a basic buffer. So I take ammonia, okay, and I will react this with a strong acid like HCl, because this will actually combine to give you NH4Cl. Okay, it's a very simple synthesis reaction. So initially, I will have 1 mole of this. Again, same as method 1, I'm going to have half the amount. And initially, I have none of these because I haven't mixed them yet. And once I mix them, just like what we saw, this is 1 to 1. This guy is limited. So I'm going to use this all up. I'm going to react with half of these. So I'm going to drop half a mole here. I'm going to drop half a mole here. Okay, which means I'm going to gain half a mole here. Okay, so at equilibrium, I'm left with half a mole of ammonia. I have no more hydrochloric acid left. And hey, I have 0.5 mole of NH4 plus, because this guy readily dissociate to give you that. Okay, again, here's my buffer at equal amount. So that's how you make them. It's by taking what you want, the weak acid that you're interested in, and react it with a strong base. Or you take what you want to make your weak, your basic buffer with. You take that weak acid, so weak base, and you react it with a strong acid. But the trick here is, whatever weak acid you're going to use, you are going to use half the amount, molar amount, of base. You know, 1/2 of the amount of your strong acid. Sorry, half the amount of your weak base and half the amount of your weak acid. I have no idea what I just said, but hopefully the number says it all. All right, so that's what a buffer do, and that's how you make a buffer. And let's take a look at titration curve, because this will lead me straight to looking at how to produce one of these, okay, in my next lesson. So what I have here is a strong acid, strong base titration curve. Now, you've done a titration before. In what we did is, if you have an unknown concentration of acid and you want to know, and you will titrate it with a known concentration of a base, okay? And if this is your starting point, obviously, you are going to be at a pH very, very low. Okay? So as you add this drop by drop, drop by drop, and drop by drop, you're going to start producing KCl. You're going to start producing H2O. Well, as you add this drop by drop, you can see that the pH will start to go up. But it's not going to go up fast though. You'll see a point where it actually goes up very, very, very slow. But when it gets near the equivalent point obviously is right here. This is the point where the mole of HCl will equal to the mole of KOH, or at least approaching it. You'll see a very, very sharp turn of pH. Okay? And there's going to be another second sharp turn where you kind of already overshoot, where the amount of base is now greater than the amount of acid, depending on how much greater. As soon as you have a little bit of overshoot, you get this. You get another sharp turn. Okay? So you'll notice that in your pH meter, okay, or whatever that you're using to measure pH, you'll see it being pH 1, and it will stay at pH 1 for a while. It's not going to go up that much, but as soon as it hits around like pH 5, it's going to jump very quickly all the way to like pH 11. Okay? As you graph this, the middle of that jump is your equivalent pH. And for a strong acid reacting with a strong base, that equivalent point or that equivalent pH is usually 7. If you graph this right. Okay? KCl is a salt. It does not react with the H plus or OH minus. This guy is going to say no to H plus. It's going to say no to OH minus. So that's why this reaction will always be going this direction. And the equivalent point is always going to be 7. Because you're not going to go backwards. Okay? However, the salt that you make doesn't necessarily always have to, I guess, go this way. Sometimes it can go that way. So when it does, something else might happen, and that is something that I guess we'll talk about in the next class when we look out weak acid versus strong base, or strong base versus weak acid. Whatever I just said. I think I said the same thing. Oh well. We'll talk about this next class. Bye guys.